Concrete is everywhere, under your feet, inside your walls, holding up bridges, carrying highways, supporting skyscrapers that weigh hundreds of thousands of tons, and almost all of it depends on one gray powder: cement. Take the cement out, and ordinary concrete stops being concrete in the way the modern construction industry understands it. The rocks do not lock together. The sand does not become a solid mass. The structure does not gain the strength engineers expect. So for nearly 200 years, the basic formula has barely changed: stone, sand, water, Portland cement. Then an American company did something that sounds wrong the first time you hear it. It made concrete without Portland cement. Not a laboratory puck. Not a decorative brick. Pourable, pumpable ready-mix concrete. The kind that can arrive in a normal mixer truck. The kind workers can place using equipment they already know. The kind that has now been poured into building foundations, shear walls, slabs, columns, sidewalks, airport projects, a section of Interstate 94 in Minnesota, and even the new J.P. Morgan Chase headquarters in Manhattan. The company is called C-Crete Technologies, and according to its latest technical data, its cement-free mixes can reach more than 7,000 pounds per square inch of compressive strength at 28 days. Change the mix design and C-Crete says they can exceed 10,000 psi. That is not the strange part. The strange part is what is missing: no Portland cement. And if this technology can scale from thousands of tons of real-world pours into millions of tons, then one of the oldest industrial recipes on Earth suddenly has competition. If you like stories where the most ordinary material in the world turns out to be hiding a massive technology race, subscribe, because this is not really a story about inventing a new kind of concrete. It is a story about trying to remove the ingredient the entire concrete industry was built around. And to understand why that matters, we need to clear up something almost everybody gets wrong. Concrete and cement are not the same thing. Cement is an ingredient. Concrete is the finished material. Think of flour and bread. You would never point at a loaf and call it flour, but people point at a sidewalk every day and call it cement. A normal concrete mix contains coarse aggregate, usually stone or gravel, fine aggregate, usually sand, water, and a binder. In conventional concrete, that binder is Portland cement. Add water and the cement begins a series of chemical reactions called hydration. New mineral structures form. They grow around the sand and stone. They interlock. The wet mixture slowly hardens into the artificial rock we call concrete. That chemistry is why concrete can start as something soft enough to pump through a hose and end as something strong enough to support a bridge. Portland cement is astonishingly good at that job. Cheap, predictable, available almost everywhere, supported by more than a century of standards, engineering knowledge, equipment, and supply chains. And the scale is difficult to picture. A modern cement plant does not look like a chemistry experiment. It looks like a small industrial city. Quarries feed crushers. Conveyors move mountains of mineral. Raw material is ground into powder. Kilns stretch for hundreds of feet. Clinker comes out as glowing nodules. Giant mills grind it again. Silos hold the finished cement. Railcars and tanker trucks carry it toward ready-mix plants. Then the cement disappears into concrete that may be poured only hours later. That entire chain is optimized around one recipe. If you invent a replacement that needs completely different trucks, different storage, different mixing, different curing, and different crews, you are not replacing one ingredient. You are asking an industry worth hundreds of billions of dollars to rebuild itself around you. That is why the word drop-in is so important in this story. The closer C-Crete can make the new binder behave like the old one inside existing infrastructure, the less of the industry it has to defeat at once. Do not replace the concrete truck. Do not replace the pump. Do not replace the finisher. Replace the chemistry hiding inside the gray powder. That is also why replacing it is so difficult. You are not competing with a bad product. You are competing with one of the most successful materials ever invented. But Portland cement has a problem hidden inside the way it is made. The conventional process begins largely with limestone. Limestone contains calcium carbonate. To turn it into the reactive material needed for cement, producers crush the rock, blend it with other minerals, and heat the mixture inside enormous rotating kilns. The temperature can reach around 1450 degrees Celsius, hot enough that the inside of the kiln becomes a glowing industrial furnace. That heat requires huge amounts of energy. But even if you powered the entire kiln with clean electricity, another problem would remain. The limestone itself releases carbon dioxide when it is chemically transformed. Calcium carbonate becomes calcium oxide. CO2 leaves the rock. That is process chemistry, not simply dirty fuel. And that is why cement is so hard to decarbonize. You can replace coal, you can improve efficiency, you can capture some emissions, but the conventional recipe starts with a mineral that physically contains carbon dioxide and then deliberately bakes that carbon dioxide out. Cement production is responsible for roughly 7 to 8% of global carbon dioxide emissions by commonly cited industry estimates. That is an extraordinary number for a material most people never think about. And the reason is simple. We use an unbelievable amount of it. Concrete is often described as the most consumed material on Earth after water. Roads, homes, ports, dams, hospitals, factories, data centers, wind turbine foundations, runways. Almost every part of the built world eventually asks for concrete. So the challenge is not to invent a green material that works in one beautiful demonstration building. The challenge is to create something the construction industry can actually use, at enormous scale, at ordinary job sites, under ordinary deadlines, with ordinary workers. And this is where C-Crete's approach becomes interesting. The company's product is described as cement-free concrete, but that phrase needs one important clarification. C-Crete has not discovered a way to make stone and sand stick together with nothing. There is still a binder. What disappears is Portland cement. The company has developed alternative cementitious binders made from abundant natural rocks and industrial byproducts. The exact formulation is proprietary. But C-Crete has publicly demonstrated versions based on materials including zeolite, basalt, and granite. That distinction matters. This is not concrete without chemistry. It is concrete with different chemistry. And the strategy is surprisingly simple. Do not ask every construction company in America to replace its trucks. Do not invent a new pump. Do not require workers to learn an entirely new pouring technique. Change the powder inside the mix. Keep as much of the rest of the construction system as possible. That is what people mean when they call a technology drop-in. The new material has a much better chance if it can disappear into the old infrastructure. And C-Crete has spent the last few years trying to prove exactly that. The first major public demonstration came in Seattle in 2023. A commercial building in the Green Lake neighborhood needed a seismic retrofit. A normal project. A real building. Real structural work. C-Crete supplied cement-free concrete that was delivered through a local ready-mix company. Workers poured it into foundations and shear walls. About 60 tons in the first publicly announced pour. Then the experiment expanded. More C-Crete mixes were used at the same site. Different feedstocks. Different formulations. By the time the company demonstrated a basalt-based version in 2024, the total cement-free concrete placed at the Seattle project had reached roughly 140 tons. That is still tiny compared with the millions of tons of conventional concrete poured every year. But the important part was not the tonnage. The important part was that the concrete behaved like something contractors recognized. It arrived. It flowed. It was placed. It hardened. The building did not become a laboratory. Then the story moved from a small Seattle project to one of the most visible construction sites in America. 270 Park Avenue, Manhattan. The new global headquarters of J.P. Morgan Chase. A super-tall skyscraper rising more than 1,300 feet above New York. In July 2024, C-Crete's granite-based cement-free concrete was poured there. 12 cubic yards. A topping slab in the upper lobby. Now, be careful with that number. C-Crete did not build the entire J.P. Morgan Tower out of cement-free concrete. Not remotely. 12 cubic yards inside a skyscraper of that size is a small demonstration. And that is exactly why it matters. Construction is conservative for a reason. If a phone app crashes, you reopen it. If structural concrete fails inside a skyscraper, people can die. Engineers do not replace a century-old material because a startup has a good presentation. New materials enter slowly. A slab, a wall, a foundation, a section of pavement, something that can be inspected, tested, measured. Then repeated. C-Crete getting into a real super tall project did not prove Portland cement was obsolete. It proved somebody responsible for an extremely serious building was willing to place the material in the building. And then came a different test. Traffic. In September 2024, a section of westbound Interstate 94 in Minnesota was paved using C-Crete's cement-free material. The section opened to traffic. Cars passed over it. Heavy vehicles passed over it. Now the concrete had to deal with a completely different world. Loads, weather, water, salt, freeze-thaw cycles, vibration. The kind of repetitive abuse highways experience every day. That matters because strength is only one part of concrete performance. A material can be extremely strong in a laboratory and still be terrible concrete. It can shrink too much. Crack. React with aggregates. Allow chlorides to penetrate and corrode steel reinforcement. Lose durability after repeated freezing and thawing. Set too quickly. Set too slowly. Generate too much heat inside massive pores. Concrete has to survive a long list of boring problems. And boring problems are what destroy real infrastructure. C-Crete's 2026 technical data is interesting because it does not only list compressive strength. The company reports performance under established ASTM and AASHTO tests for setting time, shrinkage, alkali-silica reaction, freeze-thaw resistance, chloride diffusivity, and other properties. Its standard 28-day compressive strength is listed above 7,000 psi. The company says modified mix designs can exceed 10,000. Its freeze-thaw durability factor is listed above 90% under the relevant test. And C-Crete says the material can use conventional admixtures and standard finishing methods. Those are company-reported product figures, though C-Crete says the technical data has been verified by independent third parties. That qualification is important. This material has not been sitting under American bridges for 50 years. C-Crete's oldest commercial pour is only a little more than 3 years old. The company says it shows no visible degradation or cracking. Good. But 3 years is not 50. That is one of the central problems every new construction material faces. You can accelerate laboratory tests. You can expose samples to freeze-thaw cycling. You can measure chloride penetration. You can test shrinkage. But there is no machine that can instantly give you 4 decades of real weather, workmanship, maintenance, and abuse. Time has to happen. And if you want more breakdowns where we separate what the breakthrough has actually proven from what the headline wants you to believe, subscribe, because this is where the C-Crete story becomes much larger than one company's concrete. By 2026, C-Crete says more than 3,000 tons of its cement-free product has been poured across residential, commercial, and federal projects. The list includes foundations, walls, slabs, columns, driveways, sidewalks, highway sections, and projects in several American cities. That is no longer one bucket in a laboratory, but it is also nowhere near the scale of the conventional cement industry. To understand the gap, imagine that every successful C-Crete project completed so far were stacked into one enormous pile. Then place that pile beside America's annual cement consumption. The commercial demonstrations would almost disappear. That sounds like a criticism. It is actually the stage every industrial technology has to pass through. A jet engine does not go from one test stand to powering every airplane. A battery chemistry does not go from one coin cell to every car factory. A new building material does not go from one Seattle wall to every bridge in the country. First comes chemistry, then repeatability, then production, then codes, then procurement, then factories. Then decades of boring, reliable use. C-Crete has crossed some of those gates. It has not crossed all of them, but it is far enough along that the next questions are no longer theoretical. They are industrial. And that gap is the entire battle. The United States consumes tens of millions of tons of cement in a normal year. Globally, Production is measured in billions of tons. 3,000 tons can prove that a process works. It cannot prove that the process can supply a continent. Scale changes everything. Where do the raw materials come from? Are they consistent from one region to another? How much processing do they require? What happens when demand jumps 1,000 times? Can the binder be produced near ready-mix plants? How much does it cost after transport? Can contractors order it with the same confidence they order Portland cement? Can specifications be written around it? Will insurers accept it? Will public agencies approve it? Will engineers sign their names to it? That is why C-Crete's most important claim may not be its carbon number. It may be cost parity. The company says its cement-free concrete can be cost-competitive with conventional concrete. If that holds at scale, the conversation changes completely. Because construction does not buy morality by the truckload. It buys performance, schedule, risk, price. A low-carbon concrete that costs 3 times more may win flagship projects. A low-carbon concrete that costs the same and arrives from the same kind of truck can attack the mainstream. And there is another clever part of C-Crete's strategy. It is not betting everything on one exotic mineral. The company has demonstrated multiple binder feedstocks: zeolite, basalt, granite. Industrial byproducts. That matters because cement is a local business. Concrete is heavy. Transport is expensive. You do not want to ship every ingredient halfway across the country if a suitable material exists nearby. A technology that can adapt to abundant regional feedstocks has a better chance of scaling than one dependent on a rare waste stream. And America is now full of companies attacking this same problem from completely different directions. Sublime Systems, born out of MIT, is developing an electrochemical process that avoids the traditional high-temperature limestone kiln. Its first commercial facility in Holyoke, Massachusetts, is being developed for tens of thousands of tons per year. Brimstone is taking another route. It starts with non-carbonate rock and aims to produce ordinary Portland cement itself, along with other industrial products, without relying on limestone as the source of calcium. Forterra is working around existing cement infrastructure and mineralizing captured carbon dioxide into cementitious material. Terra is commercializing materials that can replace a large portion of Portland cement today and is developing a product intended to replace all of it. Different chemistry, different factories, different business models, same target: the clinker. That small gray nodular material made inside cement kilns is becoming one of the most contested substances in American industrial technology. Because if somebody can make concrete with dramatically less clinker or no Portland cement at all, while keeping the price, strength, and construction process familiar, then they are not selling a green niche product. They are attacking one of the largest material markets on Earth, and C-Crete's version may have one unusual advantage. It is already being poured. That phrase matters. Already being poured. There is a huge difference between a material that can theoretically replace cement and one that has gone through a batch plant, into a mixer truck, down a pump line, and into a real structure. Construction is full of technologies that look incredible until they meet a job site. The truck is late. The weather changes. The crew adds water. The pump pressure changes. The finishers want a different slump. The concrete starts setting. A laboratory does not care that the contractor has 20 workers waiting. A construction site does. So a drop-in material has to survive not just chemistry. It has to survive human beings. And this is where C-Crete's use of existing ready-mix companies becomes strategically important. The company has worked with established suppliers, including major concrete names on project delivery. It is not trying to build a parallel concrete industry from scratch. It wants the existing industry to carry the product. That is much harder technologically, and much easier commercially if it works. There is also a fascinating twist in the emissions story. Conventional Portland cement releases carbon during production. C-Crete says its binders avoid those process emissions and that the resulting concrete can absorb carbon dioxide over time as it cures and ages. The company estimates that replacing a ton of Portland cement with a ton of its binder can avoid up to roughly 1 ton of CO2. It also says some mixes require around 15% less water. Those are potentially enormous advantages. But again, do not turn that into the wrong headline. C-Crete has not invented a concrete road that will vacuum the atmosphere clean. Concrete absorbs limited amounts of carbon through mineral reactions. The climate value comes mainly from avoiding the emissions associated with conventional Portland cement production in the first place. That is a much less magical claim, and a much more important one. Because industrial decarbonization does not always need one giant machine sucking carbon out of the sky. Sometimes you stop creating the carbon before it exists. Remove the limestone chemistry. Remove some of the kiln burden. Use a different binder, then pour the same wall. That is the promise. But whether C-Crete becomes the company that wins this race is completely unknown. Portland cement has 200 years of momentum. It has giant multinational producers, dedicated quarries, kilns, standards, contracts, distribution networks, engineering software, building codes, supplier relationships, an entire civilization already organized around buying it. To replace even a meaningful fraction of that system, C-Crete would need manufacturing capacity far beyond anything it has demonstrated publicly so far. Quality control would have to remain consistent as feedstocks change. Costs would have to remain competitive. Performance would have to survive decades. And contractors would have to trust that the bag, silo, or tanker arriving next year behaves like the one they tested this year. Those are not side issues. Those are the industry. That is also why the current stage is so interesting. We are watching the transition from materials science to industrial proof. For years, low-carbon concrete stories lived in research papers. A new binder. A new additive. A new way to mineralize CO2. A sample crushed in a laboratory press. Now American companies are moving into highways, skyscrapers, commercial plants, ready-mix networks. Actual procurement. The argument is shifting. The question is no longer only, can you make concrete without conventional cement? C-Crete has already shown that you can make useful concrete without Portland cement. The next question is brutal. Can you make enough? And if the answer eventually becomes yes, the consequence is much bigger than greener buildings. It changes where the cement industry gets its raw materials. It changes what happens to limestone kilns. It changes which companies control the binder. It could create new manufacturing plants in regions that never had major cement production. It could turn ordinary rocks and industrial byproducts into strategic construction feedstocks. And it could give builders more than one answer to a material recipe that has barely had serious competition for generations. Think about what happened with batteries. For years, lithium-ion looked like the only serious modern chemistry. Then sodium-ion moved from laboratory curiosity into factories and commercial products. It did not make lithium disappear. It created another option. Cement may be entering the same kind of period. Portland cement is not going away next year. It may not go away in our lifetimes. It is too cheap, too proven, too deeply embedded. But monopoly at the level of chemistry is different from dominance. The moment credible alternatives exist, the industry has to compete with a future it never had to think about before. And that is why one small slab inside a Manhattan skyscraper matters more than its size suggests. Not because 12 cubic yards changed global construction. It did not. Because 12 cubic yards crossed a boundary. The material left the lab. It entered one of the most demanding construction ecosystems on Earth. Then more material went into roads. More went into foundations. More went into ordinary projects. 3,000 tons becomes the next proof point. Then 30,000. Then 300,000. Then, maybe, millions. Or maybe the technology stalls. Maybe costs rise at scale. Maybe another American cement technology wins instead. Maybe Portland cement producers adopt pieces of these ideas and remain dominant. That uncertainty is real. But the old assumption is already weaker. For generations, concrete and Portland cement were so tightly linked that most people use the two words as if they meant the same thing. They do not. And America is now proving that distinction in the most physical way possible. Pour the concrete. Let it harden. Drive trucks over it. Build on top of it. Then ask what is missing. No Portland cement. That is the breakthrough. Not that America invented concrete. Not that cement is dead. Not that every building tomorrow will be made from C-Crete. Something more believable happened. A 200-year-old industrial recipe finally got a serious alternative that can be delivered in a concrete truck. And if that alternative survives the only tests that really matter, time, cost, and scale, then one day the strangest thing about cement-free concrete may be that we ever thought concrete needed Portland cement in the first place. Subscribe if you want more documentaries about the American machines, materials, and factories quietly attacking the assumptions underneath everyday life. Because sometimes the biggest breakthrough is not adding something new, it is discovering which ingredient you can remove.